This is part 2 of lecture 2.4 of Math 108, More Examples of Proofs. In this video, we will give additional examples of proofs of results on divisibility of integers. We will use the following concepts. Let a, b, and p be non-zero integers. The integer p is prime if and only if p is greater than 1 and the only positive divisors of p are 1 and itself. The greatest common divisor of a and b is the largest integer d, such that d divides a and d divides b. Note that the GCD of a and b is a positive integer. The least common multiple of a and b is the smallest positive integer m, such that a divides m and b divides m. A linear combination of a and b is an integer equal to ax plus by for some integers x and y. Consider the claim the number p is prime if and only if p has no positive divisor greater than 1 and less than or equal to the square root of p. This is a biconditional sentence with components p is prime, which you may recall is equivalent to the condition that any positive divisor of p is either 1 or p, and p has no positive divisor greater than 1 and less than or equal to the square root of p, which is equivalent to the condition any positive divisor of p is either less than or equal to 1 or greater than the square root of p. We will give a two-part proof of this claim. We first prove the forward implication. We begin by assuming that p is prime. We need to show that any positive divisor of p is either equal to 1 or greater than the square root of p. To prove this, let d be an integer. We need to show that if d is a positive divisor of p, then either d is less than or equal to 1 or d is greater than the square root of p. Since this is a conditional sentence whose conclusion is a disjunction, a direct proof of this must include in the hypothesis the negation of one of the conditions in the disjunction. For this proof, we will assume that d is a positive divisor of p and that d is greater than 1. We will show that d is greater than the square root of p. Next, we prove the backward implication. We begin by assuming that p has no positive divisor greater than 1 and less than or equal to the square root of p. We need to show that p is prime, that is, any positive divisor of p is either 1 or p. To prove this, let d be an integer. We need to show that if d is a positive divisor of p, then either d is equal to 1 or p. Since this is a conditional sentence whose conclusion is a disjunction, a direct proof of this must include in the hypothesis the negation of one of the conditions in the disjunction. For this proof, we will assume that d is a positive divisor of p and that d is not equal to 1. We will show that d is equal to p. We now show the proof. Assume first that p is prime. Let d be an integer and assume that d is greater than 0, d divides p, and d is not equal to 1. We need to show that d is greater than the square root of p. By the hypothesis, d is a positive divisor of p which is not equal to 1. Since p is prime, its only divisors are 1 and itself, so it follows that d is equal to p. Since p is greater than 1, p minus 1 is greater than 0, and thus p times p minus 1 is greater than 0. So p squared is greater than p, and hence p is greater than the square root of p. Since d equals p, we therefore have d is greater than p, than the square root of p. This shows that p has no positive divisor greater than 1 and less than or equal to the square root of p. For the backward implication, assume that p has no positive divisor greater than 1 and less than or equal to the square root of p. Let d be an integer and assume that d is positive, d divides p, and d is not equal to 1. We need to show that d equals p. Note that d is a positive divisor of p and d is less than or equal to 1. It follows from the first hypothesis that d must be greater than the square root of p. Since both d and the square root of p are positive, 1 over d is less than 1 over the square root of p. Since p is positive, multiplying each side of this inequality by p yields p over d is less than p over the square root of p, which is equal to the square root of p. Now, p over d is positive since both p and d are positive. P over d is an integer since d divides p, and p over d times the integer d is equal to p. So the number p over d is also a positive divisor of p. Since p over d is less than the square root of p, it follows from the first hypothesis that p over d is equal to 1. Therefore, d is equal to p. So p has no positive divisor other than 1 and p. Hence, p is prime, which completes the proof of the backward implication and the proof of the claim. For the next example, we will use the result known as the division algorithm. This states that for any integers m and n with n non-zero, there exist unique integers q and r such that m is equal to n times q plus r, and r is greater than or equal to 0 and less than the absolute value of n. We will prove the division algorithm later in the course. Consider the claim, the smallest positive linear combination of a and b is a common divisor of a and b. Let us denote by L the smallest positive linear combination of a and b. Then the claim is equivalent to the conjunction L divides a and L divides b. Hence, our proof consists of two parts. First, we will show that L divides a, which is equivalent to the condition that a is equal to the product of L and some integer k. To prove this, we will give a specific k, verify that k is an integer, and show that a is equal to L times k. Next, we show that L divides b, which is equivalent to the condition that b is equal to the product of L and some integer. The proof of this part uses the same arguments as for the proof of part 1, with the integer a replaced by the integer b. We now give the details of the proof. Let L be the smallest positive linear combination of a and b. By the division algorithm applied to the integers a and L, there exist unique integers q and r such that a is equal to lq plus r, and r is greater than or equal to 0 and less than or equal less than the absolute value of L. Note that the absolute value of L is equal to L since L is positive. Take Q to be the integer R. we are to show that A is equal to L times K. A equals L times K is equivalent to A equals L times Q, which is equivalent to the condition that R is equal to 0. Hence, we shall show that R is equal to 0 using proof by contradiction. Suppose that R is non-zero. Since R is non-negative, it follows that R must be greater than 0. Since L is a linear combination of A and B, L is equal to AX plus BY for some integers x and y. Hence, we can write R as A minus LQ, which is equal to A minus quantity AX plus BY close quantity Q, which is equal to A times 1 minus QX plus B times negative YQ. Since the sum and product of integers is an integer, 1 minus QX and negative YQ are both integers. Thus, R itself is a linear combination of A and B. In particular, R is a positive linear combination of A and B. Since L is the smallest positive linear combination of A and B, R must be greater than or equal to L. Recall that from the division algorithm, R is less than L. So both conditions R is less than L and R is greater than or equal to L hold. Contradiction. It follows that R must be 0. So A is equal to LQ plus 0, which is equal to LQ, which is equal to LK. This proves that L divides A. Replacing A with B in the preceding arguments shows that L divides B. So L is a common divisor of A and B, which completes the proof. Consider the claim, the smallest positive linear combination of A and B is the greatest common divisor of A and B. Again, let L denote the smallest positive linear combination of A and B. The claim is the statement L is equal to GCD of A and B. We will use the following facts. For any real numbers x and y, the condition x is less than or equal to y and x is greater than or equal to y is equivalent to x is equal to y. This statement can be proved using propositional calculus and the trichotomy axiom for real numbers. If A and B are positive integers and A divides B, then A is less than or equal to B. The proof of this statement is left as an exercise. Any common divisor of integers A and B divides any linear combination of A and B. The proof of this statement is also left as an exercise. The claim is therefore equivalent to the statement L is less than or equal to GCD of A and B, and L is greater than or equal to GCD of A and B. Hence, our proof will consist of two parts. First, we show that L is less than or equal to the GCD of A and B. And second, we show that L is greater than or equal to the GCD of A and B. This implies that L is equal to the GCD of A and B. We now give the details of the proof. Since the proof is short, we will no longer label parts 1 and 2. Let L denote the smallest positive linear combination of A and B. By example 6, L is a common divisor of A and B. So L is less than or equal to the greatest common divisor of A and B. By exercise 5, any common divisor of A and B divides any linear combination of A and B. So in particular, the greatest common divisor of A and B divides L. Since both the GCD of A and B and L are positive, it follows from exercise 2 that the GCD of A and B is less than or equal to L. We have shown that L is less than or equal to GCD of A and B, and L is greater than or equal to the GCD of A and B. Therefore, L is equal to the GCD of A and B. This completes the proof. You have come to the end of Part 2 of Lecture 2.4. You may now proceed to Part 3. Thank you for your attention.